everyone. Welcome to our program on TCRB, the Blaze Star. My name is Michael Sibbernsen. I'm a lecturer of physics and astronomy. I'm also the co-founder and the director of higher education for Branched Oak Observatory. It's my pleasure to present about this amazing topic to all of you. I've actually put together, I think, a very nice program regardless of your background in astronomy, whether you are just starting yourself or whether you are a seasoned astronomer. We should have a little bit of information that will be perfect just for you. We're actually going to start with an introduction to variable and binary star systems, just to kind of catch everybody up to the same point about this type of star system. Then we'll look specifically at TCRB, aka the Blaze Star itself. We'll look at how to locate TCRB in the night sky. So again, whether you're a seasoned astronomer or not, I'll show you some very detailed instructions on how to find the constellation that this star is within, and if you have a telescope or a pair of binoculars, how to actually locate that very star, or at least the location of that star within the constellation itself. Then we'll talk a little bit about the importance of recurrent nova research, and at the end I actually have one other thing that I'm going to put in there that I think you will find very, very interesting. In this great pantheon of stars that we have in the Milky Way galaxy, we have a great variety of stars. We have stars that are much larger than our own sun. We have many stars that are much, much smaller. Cooler stars, hotter stars, and within those different temperatures, we have a variety of different hues, from reds and oranges and yellows to different hues of blue. And this all comes down to their mass, and we'll talk a little bit about that here in just a moment. There are some stars, in fact, it's believed that the majority of stars in the sky are variable to some extent. But there are other stars, called variable stars, that change their luminosity over a shorter period of time. And these two fall within two families, generally intrinsic variable stars and extrinsic variable stars. The intrinsic variable stars, essentially we're talking about something internal is causing an actual brightness change within that particular star. Whereas with the extrinsic variables, we're looking at an external element, maybe an obscuration of the star's brightness itself that creates that variability. Within the intrinsic variables, we have pulsating variable stars, and here you'll find your RR Lyrae and Cepheid variables. There are others, but these two names maybe you've heard of. These are among the more popular of the pulsating variables. And then we have our cataclysmic variable stars like supernova. Now with a pulsating variable star, let's talk a little bit about that. But first, let's take a step back. This chart here, I imagine many of you recognize. This is the HR diagram, the Hertzsprung-Russell diagram, where we have essentially graphed out stars on the X and Y axis according to their luminosity, according to solar luminosities, and their specific temperature, their color temperature. And when we do so, we see this line that's created, and this line here is called the main sequence. Where a star falls on the main sequence is completely dependent on its mass. Actually, everything about a star really comes down to its mass. How it's born, how it lives its life, how it dies, and everything in between. The lower mass stars will be cooler, and they'll be in this part of the main sequence, and the hotter stars will be way up here, much, much larger in this part of the HR diagram. Towards the end of a star's life, it starts to peel off of the main sequence to the right. And this is actually where we find our giants and our supergiants. And where they fall in this range, again, comes down to what the original mass of that particular star was. Now there's a part off of the main sequence, really in between these ranges here, called the instability strip. And if a star, and this is again is at its end of its life, it spends 90% of its life there on the main sequence. And then that last part, it peels off into the upper right part of the HR diagram. And if it peels off and it falls within the instability strip, then that star becomes or has the potential of being unstable. The hydrostatic equilibrium between the outward force of energy and the inward force of gravity is compromised. It gets hotter, larger, smaller, fainter. It actually gets fainter as it gets larger because of the surface temperature. Then as it pulsates, it gets smaller, and then the surface temperature is actually hotter. It's almost like the star is breathing in and out, pulsating, changing its brightness. That would be a pulsating variable star. RR Lyrae pulsating variable stars have periods of just hours, whereas the Cepheid variables can be days up to months in their variability. And these stars, by the way, are very important to astronomers because we use these as standard candles to be able to determine the distance to stars. So these pulsating variables, very important in the field of astronomy. Then we have our cataclysmic variable stars. Here we have a star that has gone giant. It's a giant or it's a supergiant, and this particular star it's already run through its a maze of different elements, and it gets up to iron, and at that point it is no longer able to fuse. See, these very, very large stars fuse a variety of different elements within their core. Stars, of course, are element factories. But once it gets up to iron, it's no longer able to fuse it. And without that outward force keeping it outward, the inward force of gravity causes it to collapse and then go supernova. That would be our cataclysmic intrinsic variable. With extrinsic variables, we have eclipsing binaries and some very interesting rotating stars, which we'll talk about here in a moment. With an eclipsing binary star, we have two stars that are orbiting around a common center of mass. It's actually believed that a great majority of stars in the sky are binary or multiple systems. Our sun is just one of those odd men out that doesn't have a binary or multiple star pair or family of stars. These are orbiting around a common center of mass, but in this particular case, the two stars are a little too far away for us to be able to resolve them optically in a telescope. But we can tell that it's a pair of stars because of a change in brightness. Here, and here, when the two stars are side by side, they are at their highest brightness. Here, here, and here. But then as one star passes in front of the other, depending on the size, depending on the temperature, we will have different dip depths and also different dip sizes and shapes as well. So once again, we're able to tell that this is a binary system because of the brightness change of these particular stars. We also have rotating stars, and in this case, most stars are probably rotating, but here we have a star that has a very thick conglomeration of sunspots. We'd call these star spots in this particular case. And when this star rotates, a good deal of the star's photosphere is obscured from view, and the total brightness actually starts to wane and changes, gets brighter and fainter. We also have stars that might be ellipsoidal in shape, kind of an odd shape, and when these things are rotating, we are just privy to different amounts of the surface area of that particular star, and therefore we see a particular brightness change. Well, today we are here to talk about a star system, a binary system called TCRB. This is T, as in the letter alphabet. The T is part of a designation that's given to it for being a variable star. Variable stars have designations that range from R to Z, and then they start over again to RR to ZZ, and then there's also some V's with numbers behind it. This particular one is T, and the CRB is essentially Coronae Borealis, the Latin genitive for Corona Borealis, the northern crown, the constellation that this particular star is within. TCRB is also known as the Blaze Star. This was a nickname that it was received by an author named Admiral Smith, who wrote about the star suddenly blazing forth in 1866, causing quite a stir within the astronomical groups at that particular time, and the nickname stuck ever since. It is a spectroscopic binary. Once again, here we have two stars that are too far away for us to be able to visually separate. Whenever we are unable to optically separate them in a telescope, we name that binary system, that multiple star system, after the method that was used to determine that it's a binary star. In this case, it is a spectroscopic binary because we're using a spectroscope and we're looking at the spectrum of these two stars. At first, it just looks like a single spectrum, but we look very carefully at the dark line, the absorption lines within that spectra, and we'll see some motion back and forth as one star, maybe the brighter star, or we can see two of them going back and forth, passing each other like so, as one star is red shifted and moving away from us, and the other star is blue shifted moving towards us, because these two are on the same plane with our own line of sight. This again would be a spectroscopic binary. This particular system is about 3,000 light years away from us. It's made up of two bodies, a white dwarf. This is about the size of the Earth, believe it or not, and it has a mass of 1.37. This M here is for mass, and then the little circle with the dot in the middle, that represents our own sun. So this is solar masses, 1.37 times the mass of our own sun within a region the size of the Earth. The second star in this pair is an M3 red giant. This is about 75 times larger than the sun, and look at its mass. 1.12 solar masses. So yes, that little white dwarf is more massive than that giant red star. They have an orbit around their common center of mass of about 228 days. To put that into perspective, that's about the distance, or that's about the orbital period of the planet Venus. And they have a separation of, it sure doesn't look it in this particular graphic, but they have an actual separation of about 0.54 astronomical units. That would be half the distance between here and the sun. When we have two bodies that are this incredibly close to each other, the white dwarf pulls atmosphere off of the red giant into an accretion disk. Some of that material falls onto the white dwarf into a shell, and at the interface, it starts to heat up. And after enough time, it ignites in a runaway thermonuclear eruption. Both the white dwarf and the giant they survive this eruption, and the process starts all over again. Now, while we certainly have some outside influences, that fuel is coming from an outside star, this is considered, because of the eruption is happening on the surface of the white dwarf, this is considered an intrinsic variable. This is an eruptive intrinsic variable. There's our novae, compared to the cataclysmic intrinsic variable, the supernova. Recurrent nova. A recurrent nova is a nova that, well, reoccurs. It goes nova, and then it builds up that material, builds up that heat, builds up that energy over a certain amount of time. Then finally, another thermonuclear explosion, and it goes nova again, and it does this over and over. It is believed that all novae are recurrent novae. However, many of them have periods of, well, tens of thousands of years. In our current lexicon, we now reserve the term recurrent nova for stars that we have actually seen, that we've actually recorded going nova, particularly within less than 100-year time slot space. This one is a recurrent nova, and, well, out of all those hundreds of billions of stars in the Milky Way galaxy, how many recurrent nova do you think that we have recorded? Hundreds of billions of stars. 10. That's it. Just 10. There are probably more, and we just haven't recorded those yet, but 10. And here they are. Now here we're able to see the names on the far left of each of those recurrent nova, and in red we have T Coronae Borealis. You'll see the name of the discoverer in the next row, and then you'll also see in the next column we have the distance. We can see our distance of T Coronae Borealis at 2,987 light years, so nearly 3,000 light years. The next column is our magnitude range, 2.5 to 10.8. Now, just as a quick refresher, each jump in magnitude, whether you're going greater or less, is a difference of 2.5 times. So between 1 and 2 would be 2.5 times brighter or fainter, depending on which direction you're going. And here's where it gets a little odd. As you probably know or probably remember, the smaller numbers are brighter, the larger numbers are fainter. So here we can see our range is 2.5. That would be at its absolute brightest, whereas 10.8, around 11th magnitude, would be the average brightness of T Coronae Borealis under normal conditions. This is quite an amazing range. Next to it, in the next column, we see that it takes 6 days, less than a week, to drop 3 magnitudes. Remember, that would be 2.5 times 2.5 times 2.5 times fainter. So, long story short, within just a week after it goes nova, it will drop so much in brightness that you will just barely be able to see it with the unaided eye. So, if you hear anything on the news, or any of your friends tell you that T Coronae Borealis has gone off, you must go out that night, or at least the following night, hopefully the weather will be good, and take a look at this incredible, incredible event. Also, I encourage you, if you see it yourself or you hear about it, email your friends, maybe even call your friends, wake them up. Don't worry, they won't mind at all, because this is such a special, special event. You will want to be able to see this with the unaided eye right there in the night sky. Next to it, we find the known years of eruption, and we can see that we have recorded T Coronae Borealis going nova 4 times now. The interval is pretty regular at about 80 years, and the years since last eruption was 79. So, when's it going to go off? Well, according to this chart, well, next year. Let's talk a little bit more about that in a moment. But I do want to bring something very, very important to your attention here. According to this chart, T Coronae Borealis is the closest. It's the brightest in terms of when it goes nova, but also brightest when it is at its faintest. So that means that it is within the range of more amateur and professional observatories. It is among the most regular in its eruption out of all 10 of these recurrent nova. And of course, according to this, it is ready to erupt. So when? When is this going to happen? Well, if you have been following T Coronae Borealis, you know very well that astronomers got very excited about it possibly going nova last year, 2024, at the time of this recording. And we were very excited about it going off, and well, it didn't happen. Why did we think that it was going to go nova last year? Well, I'll show you why. But first, let's take a look at a chart from the TCRB eruption in 1946. What we're able to see here is that it had 1 year prior to erupting in 1945, it started a pre-eruption dip in magnitude, got fainter and fainter and fainter, and then about a year later, boom, this thing went right off of the chart, figuratively and literally in terms of magnitude. Well, on June 29th, 2023, the AAVSO, this is a variable star observers group here in America, the American Association of Variable Star Observers, who have, believe it or not, nearly 500,000 observations of this particular star. They noticed a pre-eruption dip. They saw it. This gave them a prediction date that the eruption should occur around 2024.4 plus or minus 0.3. That would put it between mid-January and August. And we watched, and we waited, and we watched, and we waited, and it never went off. So what happened? While astronomers can try and predict a potential eruption based on historical patterns, nova events are inherently complex and unpredictable. The exact timing can vary, and obviously that's what happened in this particular case. So the question is, when is it going to happen? What are they saying now? Well, here we have a few observatories and scientists this is Thuringen State University in Germany. They stated this, and this, by the way, is about a month ago. Just a month ago from the time of the taping of this particular program in mid-March of 2025. We have noticed significant changes in the spectrum of T Coronae Borealis over the last 2 weeks. The emission lines in the spectra have risen sharply, indicating a greatly increased accretion rate. Furthermore, emission lines can now be seen that only occur at a temperature of at least 40,000 Kelvin. These could be the first signs that the nova is about to erupt. Soon after, on the Astronomer's Telegram, this is an informal correspondence between astronomers, we see this from India and Ethiopia. A very, very similar explanation. The rate of flux increase has drastically risen in recent days. But here is what I find most interesting. I have it underlined. A similar trend was observed in the later stages of RS Ophiuchi prior to its 2021 outburst. This was another recurrent nova. We saw this prior to it going nova. Given the rapid and drastic increase in intensity and width within the hydrogen alpha profile, so they're basically looking in a very narrow bandwidth of the electromagnetic spectrum, 656 nanometers, we strongly anticipate that the TCRB outburst may occur soon. These folks are sure that this star is going to go nova at any time now. So, do we have another red herring? Do we have another wild goose chase like we did last year, perhaps? What can we do about it? Well, the only thing we can do, and that's just sit back, relax, look up, watch, and observe. Now let's discuss exactly how we locate the constellation of Coronae Borealis and the location of T Coronae Borealis, the blaze star. Well, here we have the constellation of Coronae Borealis, kind of a bowl-shaped constellation, and each one of these stars is a jewel in the crown. Coronae Borealis literally means the northern crown. Each star is a jewel, and the brightest jewel of the bunch, its name is Alphecca. It also goes by the name Gemma. And yes, that is where we have derived the name gem from, for a jewel. The same place that Gemma came from. This is a beautiful constellation in the sky, but it is relatively small. And the best time to view it is a little bit later in the year. Right now, it's a little bit early to see, but you can see Coronae Borealis if you're going out after midnight. Let's say about 1 in the morning between March and late April. If you are viewing this video later in the year, let's say around the middle of summer, Coronae Borealis is going to be very high in the sky, darn near at your zenith. But I'll show you some methods that you can use to find it regardless of where it's located. You can also use any of the planetarium apps on your phone to be able to locate the constellation. Coronae Borealis at this particular time, 1 in the morning between mid-March and late April, is going to be in the east. Depending on the exact time you're going out, it might be higher or lower in the east. It is right next to a very bright star in the sky named Arcturus. Arcturus is in the east-southeast, and I'll tell you, you can't miss it. It's the second brightest star in the entire northern celestial sphere, and it's the 4th brightest star in the entire night sky. Very, very bright. But if you're the type who thinks you can miss it anyway, let me show you a very, very easy way to find the star Arcturus. First, locate the asterism of the Big Dipper. Big Dipper is, of course, inside of Ursa Major, the Big Bear, but the Big Dipper itself is very, very easy to locate in the night sky. But do remember that the orientation of the Big Dipper is going to depend on the time of year and the time of night that you go on out. At this time, it's very, very high in the sky on its side. There's the cup and the handle of the Big Dipper. We're going to use an ancient astronomy mnemonic for star hopping to locate Arcturus. Follow the arc of the handle of the Big Dipper to Arcturus. So find the Big Dipper, follow the arc to Arcturus, and there it is. Coronae Borealis, the northern crown, is right next to Arcturus. Arcturus is in the constellation of Boötes, the herdsman, and next to Coronae Borealis on the other side is Hercules. Soon, the entire summer triangle will be coming up in the northeast. So once you have found the northern crown in the night sky, we need to go to the next step. Each one of these stars, of course, has a numerical designation and, in this case, a Bayer designation. The brightest star is the alpha star. Alpha, beta, gamma, delta, epsilon, theta, eta is actually over here, and iota. The stars that we're going to concentrate on will be from one down from the end of Corona Borealis on the left, Epsilon Coronae Borealis and Delta Coronae Borealis. Let's go ahead and zoom in on those two stars. The distance that these two stars have from each other is going to play a very important role visually in the sky. What I'd like you to do is to look at the space right in between those two stars and look at the distance that that space makes. Now go towards Epsilon Coronae Borealis and down that distance the exact same amount, and we have located the location of TCRB. Now I know this seems difficult, but we'll show you some other methods here in just a moment, but I do want to show you something very, very important. We've pointed out TCRB here. I'm going to zoom out, keeping that arrow there. Now you'll notice it is going to be extraordinarily difficult to find this in the actual sky. As a matter of fact, it is too faint to be able to see. You'll be able to find these crown stars very easily. But locate that distance between the two stars, our Epsilon Coronae Borealis, Delta Coronae Borealis, go over to Epsilon Coronae Borealis and then down the same distance, and in that region you should have it within that field of view of where T Coronae Borealis is located. But I do want to point out something important. This star right here, its name is, and let me circle it in yellow, is named Variabilis Coronae Borealis. It too is a variable star, and an amazing variable star. We'll talk about that some other time, but what I want to point out with Variabilis Coronae Borealis is that its magnitude is 6th magnitude. And if you are in astronomy, you know very well that 6th magnitude is important, because 6th magnitude marks the very faintest stars that you can see with the unaided eye. That means that if that is the faintest star that you can see in the night sky, even with extraordinarily dark skies, like at Snake Campgrounds at Merritt Reservoir during the Nebraska Star Party, if that's the faintest star you can see, that means that the majority of stars that you see on this particular image, you cannot see with the unaided eye. The easiest ones are going to be the stars here. Another star that I'd like to pay attention to here is, once again, Alphecca, Gemma. The reason being is that not only is it extraordinarily bright, its magnitude at 2.22 is about the magnitude that T Coronae Borealis will be when it goes nova. Can you imagine that? So while this might be difficult to locate the exact area of T Coronae Borealis right outside of the constellation of Corona Borealis, if that star has gone nova, it'll be a piece of cake to see. It will be this bright, and you'll see a new star appear right to the side, the left side of the bowl of Corona Borealis. This is why astronomers are so excited to see this new star appearing in the sky. Let's take a look at another method that astronomers here will really appreciate. You'll probably recognize this particular red circle, this bullseye, and if you don't, let me explain what it is. This is a device that astronomers use called a telrad. It's essentially a finder scope, a zero magnification finder scope that clicks onto the side of a telescope. And when we turn it on and then look through the glass here, we can see a little red bullseye just floating there. And when we point our telescope up and we look through the telrad at just the right angle, we can see this zero magnification bullseye, this heads-up display floating among the stars. And we just place that wherever we want to look in the night sky, and then we look through the eyepiece and hopefully we'll have what we were looking for. The outside of a telrad reticle is 4 degrees. 4 degrees. The inside circle is 2 degrees, and the inner circle is 1/2 of a degree. This is the size of the telrad reticle right inside of the bowl of Corona Borealis. Let's use this to help us find the location of T Coronae Borealis. Step 1 is to move our reticle down to Epsilon Coronae Borealis. When you look in your telescope, you should see a very, very bright star right there in the center, and you might want to go ahead and center that star within your field of view. At this point, you'll notice that Delta Coronae Borealis is on the outer circle, and the location of T Coronae Borealis is right there on the intermediate circle. Isn't that something? Now, with a very steady hand on maybe a manual telescope like a Dobsonian, or on the electronic control of an electronic telescope, slowly move that reticle downwards at a right angle. Now, Epsilon Coronae Borealis is on that mid-circle, and T Coronae Borealis, or at least the area, should be right there, not only in the center of your telrad view, but hopefully within the center of your view in the telescope itself. When you look in your eyepiece, the magnification is going to completely depend on the magnification of your system, the eyepiece that you're using. But you should see a very definite triangle within that view, and then center that triangle. The tip of the spear, so to speak, the tip of that triangle, that is it. There it is. There is T Coronae Borealis. Let's take a look at another popular method to find it, or at least it's a method that I found. It's very popular, of course, to use electronic telescopes, and if your telescope has the T Coronae Borealis within its memory, fantastic. You just plug that in and go right to it. Not all telescopes will have it, however, in their catalog. Lately, smart telescopes have really become all the rage. This is a very popular smart telescope from ZWO. This is the SeeStar S50. SeeStar, S-E-E-S-T-A-R. The S50, 50 for the 50 millimeters of its aperture. I know it doesn't look much like a telescope, but it really is amazing. This goes on a small tripod that you set up, and then the arm moves upwards and then points at whatever object, deep space object, you want to look at, including planets and the moon as well. And you control it using your phone, or you control it using a tablet. Not only do you control it using your tablet or phone, you also observe using your tablet and phone. It does not have an eyepiece. It transmits the image up, but not just a live image, it actually stacks 10-second images on top of each other. And I'll tell you, after just 30 seconds, that little telescope outperforms all the telescopes out here at Branched Oak Observatory. And in just 5 or 10 minutes, you have images of galaxies, nebulae, star clusters that, well, rival the pictures that you'll find in an astronomy book. They really are amazing. And that particular telescope, the SeeStar, is so popular because it's relatively low price point and its high performance. But the one thing that really bothered me was TCRB was not in the catalog for the SeeStar. And then on top of that, the SeeStar, you are unable to plug in right ascension or declination coordinates. That's the coordinate system that astronomers use to find deep space objects in the sky. So, had to come up with what the kids would call a hack. Came up with a little trick. So if you have a SeeStar, here is a very easy way to find TCRB. Let's zoom in again. And remember, we're halfway here. Over, down, there's our triangle, and there is TCRB right there. Next to TCRB, right here, is a very, very, very faint object. Not a star. Believe it or not, that's an extraordinarily faint galaxy. Its name is IC 4587, and that galaxy is in the catalog of the C star. So if you have that particular telescope, or if your smart telescope has this object in its catalog, you just plug in IC space 4587. The telescope will then move right to that space, and you'll get a view similar to this. This, by the way, is a 74-minute image. This is a very, very long exposure because that particular galaxy is extraordinarily faint. We have nearly centered that galaxy within the field of view of the C star, and to find T Coronae Borealis, just simply look for the brightest star near that galaxy. And there it is. There's T Coronae Borealis, and there's that telltale triangle in the sky. That's the magnification, or at least the scale, that you'll see with the C star telescope. A very, very fun, easy to use trick to find TCRB easily in the night sky. T Coronae Borealis and recurrent nova research. Why is this such an important event to us amateur astronomers? Why is this so important to professional astronomers? Well, really for everyone. This is a true once-in-a-lifetime cosmic event. Lately, we have been privy to some amazing, beautiful astronomical events. Aurora at extraordinarily low latitudes, annular eclipse in 2023, a total solar eclipse in 2024. And as rare as those are, they simply do not hold a candle to how rare an event something like this is. It truly is once in a lifetime. But it's also a cosmic event for everyone. Yes, the brightness of 2.2 or around second magnitude might not seem extraordinarily bright in the sky. It is bright enough that everyone can see it if you know where to look and you have clear, dark skies. Everyone can participate in this amazing cosmic event. For professional astronomers, it's very, very important as well. Observing an eruption in real time provides direct insights how mass transfer from the companion star triggers these outbursts, providing us a better understanding of astrophysical processes. Studying TCRB helps test theories on whether recurrent nova contribute to white dwarf growth, bringing them closer to the supernova threshold. We'll actually talk about that towards the end of the program, which is coming up very, very soon. And the 80-year cycle of TCRB allows astronomers to test and better refine models predicting the timing and energy output of nova events. So that means that for other recurrent novas, we'll be able to predict those with even better accuracy. Different observatories allow astronomers to study the nova in multiple wavelengths. Optical, X-rays, radio waves, we're able to see this all at the same time. And that's the other reason this particular recurrent nova, TCRB, is so special, because it's so bright. We are able to observe it over a large array of different wavelengths that just makes it that much more important, revealing information about shock waves, ejected material, and accretion dynamics. Recurrent nova like TCRB provide a direct look into the late stages of binary star development and a better understanding of stellar evolution as well. And speaking of stellar evolution, that brings us to the end of the program, this little added bit that I wanted to talk about. The possibility of an even bigger show coming out of TCRB. Here we can see the very basic evolutionary development of smaller and more massive stars. Smaller sun-like stars will become red giants. They will fuse different elements. They'll get up to carbon and then finally dump that carbon into their core. The outer shell of the star will then slough off into space, creating a planetary nebula. The core of the star will collapse into a white dwarf, much like the white dwarf that we've been looking at in our TCRB system. Larger stars have some similarities, but some differences. Here we have a very bright blue OB type star going into a red giant. But here that star is massive enough that it's able to fuse even heavier elements. And it fuses those heavier elements up until the point of iron. That star goes supernova. We talked about this earlier. That's actually a type 2 supernova. There is another type that we'll discuss here in a moment. That core then collapses past the white dwarf stage into a neutron star. And if the original star was massive enough, it might even collapse past the neutron star stage into a black hole. But there is another type of supernova, the type 1A supernova, that is actually related to a white dwarf. The size or the mass of the white dwarf is related to something that is called the Chandrasekhar limit. Here we see the Chandrasekhar limit. This is as massive as a star or the stellar core can be and still be considered a white dwarf. And while this might look somewhat complex, if we put in all of the universal constants here, the gravitational constant of the universe, Planck's constant, the speed of light, we put all those in, we get a very, very easy to understand number. The Chandrasekhar limit is 1.4 solar masses. If a white dwarf is greater than 1.4 solar masses, it's not a white dwarf anymore. The degenerative pressure is no longer able to hold that star up and it collapses. Remember what TCRB, the white dwarf, what its mass was? We believe it's about 1.37 solar masses. That is spectacularly close to the Chandrasekhar limit. And it's got a binary pair. It's pulling material off to form that nova explosion. But it's not just the energy, it's also the mass, dumping that mass onto the star itself. What would happen if it not only pulls off that material and it adds that mass beyond the Chandrasekhar limit? Well, like a nova, it heats up and it goes nova, but in this case it goes supernova. And a type 1A supernova is brighter, is actually much brighter than a type 2 supernova. It'll be 6,000 times brighter, 6,000 times brighter than the nova, 160 times brighter than the brightest star in the night sky, and 11 times brighter than the planet Venus. And if you've ever seen Venus, you know how extraordinarily bright Venus is in the sky. 11 times brighter than that. So incredibly bright, you would be able to see T Coronae Borealis going supernova during the daytime. That's pretty exciting. Will T Coronae Borealis go supernova this time around? Probably not. It's probably an event that will happen, but sometime in the future. But it sure is fun to think about. So let's keep our eyes on the sky. For when TCRB erupts, we will be part of something truly extraordinary. Witnesses to a celestial event that will bring together and unite astronomers and dreamers and star watchers from around the world. This is our moment to experience a universe in motion. So don't miss it. Thanks so much.